Good afternoon, everyone. My name is John Laris, and this is my take on the distribution system planning study. So one last reminder of why we're all here. We had 3 tasks for this distribution system planning. The first one was a snapshot simulation to get an overview of OpenDSS and how it functions. The next task was to provide a voltage profile along with currents for each line segment and losses for the entire feeder in the snapshot mode. And lastly was to switch to the 24-hour daily mode simulation. From there, we were to determine the sustainable load growth percentage, then implement distribution generation in the form of PV panels, and then from there we had to resolve voltage magnitude violations. So task 1 was very straightforward. It was simply executing the pre-provided 13-node feeder circuit in OpenDSS. And from there, you can determine the minimum and maximum voltages right away, as shown on the right near the top. And then you can also show the real and reactive power and the losses on the entire feeder. Task 2 is where things got a little more interesting. Here's where I plotted the voltage profile straight through OpenDSS. You'll notice that the top red line and the bottom red line correspond to 1.05 and 0.95 per unit voltage, respectively. And here there are no voltage magnitudes. The peak voltage is at 1.04 and the lower voltage is around 0.97 pu. Then we can determine all of the line currents for each, and from that I exported as a CSV file. That is not present on screen simply because it's just too much data to present. And last are the line losses, which are accumulated in the chart on the right, with the total kilowatt losses for the feeder being about 32.2 kilowatts and the kVA losses being about 94 kVA. Task 3 is where things started to get interesting. So this is where we had to increase the load growth factor to a maximum value without experiencing any voltage violations. And my approach to this was using the set load molt function, which allows you to just input a decimal value and slowly increment your load. And my approach to this was, increment by 1/10 of a point first, and then 100th of a point, and then 1,000th of a point. And I reached the point where increasing increasing all of the loads by just 1,000th of a percent, so 0.001, would cause a voltage violation. So the low voltage on my simulation was 0.9006, I believe. And so we are at the limit of a low voltage violation. So to resolve that, scenario 2 implements 4,000 kilowatts of a PV system, and it's actually a 4,000 kVA rated PV system, but we were given a power factor of 1, and so 100% of the real power is being delivered to the system. And this is at node 675. So from here we were to plot the load demand and PV generation, which are provided via curves, XY curves that vary their demand and supply over the period of the day. So for example, you see here that the PV generation is 0 during the first 4 hours, and during the last, 5 hours, because, nighttime, there's not going to be any PV generation, and it scales up slowly. Maybe this is like a large period of cloud, or, the sun disappears for a little while. And the convention here is that the negative sign denotes that the PV is contributing to the system as opposed to the load being a positive sign convention. And so the losses are also quite negligible. But you can see here we reach maximum generation of 4,000 kilowatts at about hour 14, and the corresponding load is not that high. And so what shows next is the voltage violations that occur on the high end, and this is, I believe, on the A phase. So because the system has not very much load and maximum PV generation at hour 14, we see a voltage violation greater than 1.06, which is very high. There is no low end voltage violation, the minimum being at 0.97 right here, but because we have that, high end voltage violation, we need to pursue operational control methods. And as well, phase B violates pretty much the entire day as well. Phase C does not. So scenario 3 is to move half of the PV generation, which is 2,000 kilowatts, from node 675 to node 680, which is on the other side of the feeder, and then replot those voltages per phase over 24 hours. And something to note is that the minimum voltages were completely unchanged, so I did not bother including them in this presentation. However, what you will notice is that the maximum voltages drop ever so slightly. So this blue line is the pre-move voltage at around 1.06. This purple line is the post-move voltage at about 1.588 per unit. So it is a drop of voltage, but it is not significant enough to bring us below the violation state. So scenario 4 is where we seek to resolve this using two different operational control methods. And so the two I selected are 3 one-phase transformer voltage regulators to include at the substation for each of the one-phase transformers that account for the 3 phases of power. And then I also implemented the inverter volt-var control. And again, we were required to plot the min and max voltages over 24 hours. So my approach to the transformer voltage regulator was very straightforward. Using the MATLAB COM interface, we can use what is called a reg control for each transformer. And it allows us to target the transformer, target the winding to be regulated. In this case, it was the 2.4 kV winding on the low side of the transformer. And then you can provide a target voltage for it to regulate to. In this case, I selected 40 because in order to reach the target output voltage of 2.4 kV, you have to divide that voltage by the PT ratio, or the potential transformer ratio, which I selected to be 60. So really, these are two flexible numbers. You can make this, say, 1,000. You can make this 2.4. You could, limits on practicality would be required to investigate, because at one point it would say a 1,000 or 2,000 to 1 potential transformer be impractical. I'm not certain about that. But I picked two slightly conservative values of 60 and 40. Multiplied together, they reach 2.4 kV, or 1 per unit. Then the inverter volt-var control is extremely simple. The first step, however, I learned this the hard way, is to increase the maximum number of control iterations. Without this, the simulation will provide errors. It might not resolve. I had mine crash a couple of times. And so I put a pretty high value of 2,000 control iterations because it was ending up closer to, say, 1,800 iterations without completing. So actually implementing the volt-var control was very simple. For one, the inverter control command varies off of an XY curve. And I named this VV curve. I believe I got this from one of the help manuals for OpenDSS. And you specify the number of points, and then the Y array is the value of the reactive power injection or taking out of the system in per unit. So, for example, 1 per unit is the full capability of the PV systems, which would be, I believe, 4 kVAR? Yes. And then the X array tells what voltage in per unit to apply that specific reactive power to. So if the voltage per unit is, terrible, 0.5, we're injecting all of the reactive power we can to try and raise that voltage back up. And even until it reaches 0.98 per unit, we're still going to inject all of the reactive power for as sharp of a transition as we can. And then once we start going above 1 per unit, which is, the perfect voltage, we start taking out reactive power using the PV system and continuing to take out the maximum at 1.5 per unit as a worst case scenario. And so inverter control, it must be set to volt-var mode, and you can provide it this curve that you determine beforehand. So the results of the transformer voltage regulators were very successful. The maximum voltage is maintained below 1.04 pu, pretty close. It's 1.03, lots of 9s. So we're getting right up on the edge, but we are not violating, which is great. And then the minimum voltage as well is maintained above 0.95 pu at 0.951. So a good little bit of room for error. The inverter control is additionally maintained below 1.04 and above 0.95, with a more healthy low-end voltage at 0.9747, and the high-end voltage is 1.03994. So we're also a little bit lower on this end. And that peak again occurs at hour 14, where the PV generation is at its maximum, and the load is not very high. And talking to that, we'll actually notice I plotted the load demand losses and the PV generation again. And the load demand and losses again are pretty much unchanged, but the PV generation curve is modified by the inverter control system. You'll notice in the early hours of the day, the PV is actually acting as a load in order to reduce voltage because of a higher presence of generation and a lower load, or a load that is increasing per se. And then we notice here towards the bottom that our peak PV generation is actually capped at 3,000 kilowatts, meaning we're using only 3/4 of our inverter capability, such that we can prevent the violations at hour 14 as shown here. We are close to that violation at hour 14, but not exceeding it. And so, concluding, I determined that the maximum uniform load growth before any violations would occur is 42.5%, which is fairly significant. The 4,000 kilowatt PV generation resolves the low voltage but causes a pretty severe high voltage violation, and splitting the PV unfortunately only reduces this very slightly. So implementation of operational control was necessary, and I chose the transformer voltage regulators and the inverter control system. And lastly, operational control did resolve all voltage violations, and it enabled me to come to the conclusion that the initial PV system was very much oversized by 25%. But if the intent was to immediately implement operational control, then that oversized low PV generation system does leave room for more growth. Thank you.